we are now going to be going through carboxylic acid derivatives and also enolates. I want to review this diagram. You want to make sure that if you're going to make any of the acid derivatives, which are listed here, you want to make sure that you go through the acid chloride. Looking at the energy diagram, the acid chloride is the highest energy compound. Right here we have the carboxylate anion, which after protonation becomes carboxylic acid, kind of like on the lower side of things, okay? So we want to make sure that we go to the acid chloride, and then if we want to make any of these acid derivatives, we go and we do that. Now what I want you to realize is when we're looking at this, we are replacing the Cl here. Looking at that, what we want to do is we want to come over here and we want to find over here what is replacing the Cl. I'm going to kind of put a little box around it. When we do that, all we have to do is add an H, whatever's in the box there. So I put R prime, C, double bond O, O, and we add, so for, you can see this, add an H. Okay. So what happens if we want to go from the acid chloride to the ester? Then what we're going to do is we're going to add R prime, O, and again, just add the H. If we want to go to the amine here, we start with NH2, and again, we're just going to add that H, so that becomes ammonia. Now, if we want to go to the carboxylate anion, what we're going to do is we're going to start with an oxygen. The only way we're going to get O- is if we have OH-. So most acids in a basic environment will deprotonated and be in the carboxylate anion formation. Afterwards, we can protonate that to get our carboxylic acid. Let's use that same criteria in looking at going from the anhydride here to the ester. So for the anhydride, what we're going to do is we're going to put, again, R prime, O, and then all you have to do is add H. We'll follow this all the way down. The next one would be an H2, add an H. And the last one again would be the O-, but we really can't have O-. So what we're going to see here is I need to come down and pick up an H over here. And now if we look at the ester only has two choices here. The first one, I'm going to use orange here, so this kind of correlates. We're going to have an H2, and again you're just going to add what? That's right, an H. And then the last one you're going to have is the O-, and again you're going to add that same H. And the last one we have is the amide here, C double bond O, NH2, going to the carboxylate anion, and we're going to come in here and we're going to put just O- and just add that H. So with this in mind, we can now start our review. Remember, want to make any of these, it's best to go from the acid chloride down to the acid derivative. What we want to do is kind of analyze what we have over here. Here we have, what is this? This is an acid chloride. So therefore, we are going to need to make this from what? The carboxylic acid. So carboxylic acid, which is C double bond O, OH, reacted with SOCl2, gives us our acid chloride. Now here, notice I put two steps in between because I'm trying to go from the acid to the anhydride. So I've boxed in what I'm adding in, and again, the SOCl2 will form our acid chloride, and then I just add an H to whatever is in the box. It looks like I'm going to a carboxylic acid. Looks like I'm starting with an ester. Right? So really to go from an ester back to the acid, really, you may either need just water, or if you want to do it the right way, probably sodium hydroxide followed by acid workup will get you the carboxylic acid. We're starting with, this is an amide, C double bond O, N, so we have an amide going to an acid, and if we remember from our chart that we started with today, all we need to do is put NaOH, will form the carboxylate anion, and an H3O plus to protonate our acid. If we start with a nitrile here, and we go to the acid, we just put in H2SO4. This is part of our one carbon addition reactions where we had already displaced, let's say, an alkyl halide with Cn-, but we can hydrolyze that nitrile with sulfuric acid. We're going from acid chloride to ester, and again we're just putting in some alcohol. All we do is we box off what's attached and just add an H to the oxygen here, so we get CH3OH. This is a tertiary alcohol, and this can actually come from one of two functional groups. It could come from the ketone. It could also come from the ester. From the ketone, we just add one Grignard, one equivalent of Grignard, CH3MgBr. But remember, we need some H3O plus in there to what? Protonate the alcohol. This is kind of a special reaction because going from acid chloride to ketone. So what we're using here is something called a dialkyl, two alkyl groups, lithium cuprate. In this reagent, the copper is in a +1 state, not our normal +2 state that we usually see copper in. And again, here we have an aldehyde, and we said that the mild oxidizing conditions for an aldehyde is Br2 in water. We'll see this reaction again when we get to carbohydrates. When we treat aldehydes with Br2 in water, it's a mild oxidizing condition, and it yields us our carboxylic acid. Notice we have a reduction. Why? Because we see an increase in the number of hydrogens in the compound. And because this compound is not an aldehyde or a ketone, we have to use lithium aluminum hydride with water. This seems very complicated down here. Realize what are we looking at here? And remember, this is what? Ethyl acetoacetate. And realize that the protons on the carbon in the middle are acidic because you're sandwiched between two C double bond O's. First reagent there, NaOET, ET for ethyl, right, is because we want to match the ending of the ester to the base we're using, so we don't get a change in our ester on the end. So NaOET, ETOH, which is ethanol, that removes a proton, creates our enolate. We react it with alkyl halide. Notice we have one more carbon here, so we just need CH3Br. The NaOH, what does the NaOH do? NaOH is in there to, this is for, what do we call this? Ester saponification. So, once we saponify the ester, we're going to have a carboxylate anion. Throw in H3O plus to protonate, right? So as we go to O minus, then OH, and then the heat does what? That's right, decarboxylation. Okay? Alright, let's go back to our review sheet now and see if we can grab another couple of questions. See how we're doing. Okay, here's another few. And if we look at this now, of course, here we have an acid to an ester. Remember we said this wasn't the most efficient way, but it's called a Fischer esterification. Notice the equilibrium arrows. Very hard to get good yield over here. We all know that because you did this in lab. We made methyl benzoate. Remember this is called methyl because of the CH3, and then because this is a derivative of benzoic acid, it's benzoate. The better way would be to take benzoic acid here, make benzoyl chloride, right? Benzoyl chloride, and then treat the acid chloride with methanol to get methyl benzoate. This is another one of our special reactions. Now, another way that we could have done this is by using the reagent dibal, the diisobutyl aluminum hydride. And dibal, again, would only deliver one H into the C of the C double bond O to give you an aldehyde. And what we see here is we're going from acid chloride to ketone again. And remember, this is that dialkyl lithium cuprate to get you to the ketone. Because there are two hydrogens here, right? When we oxidize this thing with KMnO4, OH minus, probably a little heat, we're going to get carboxylic acid on both ends. But because of the OH minus that's in here, right, you're going to get O minus on either end of this compound. And that's why we have to dump in the H3O plus. So anytime we have permanganate, base, and heat, if we have a double bond, it's going to cut the double bond in half. And we either get carboxylic acid if you start with just a proton here, or if you have an alkyl group like a CH3, then you'd end up with a ketone. What do we see here? We have a nitrile to acid, that's that hydrolysis, okay.